Hi, guys. Can you hear me?
Yeah.
Yeah.
Yep. That's a yep.
Yes, sir.
Okay. You sound real excited. You sound really, really excited today.
I am. I'm so excited. I'm ready to
I can
go.
tell. This is amazing. How are we all doing, guys? We doing
Good.
okay? I just want to check my notes in my grade book for 1 second. And good. Is Arthur here? I think he's dropped, but is Arthur here? All right, guys, from now on, all you have to do, everybody's gotten a notebook, at least one good notebook. Just keep on submitting them. I'm going to give a perusal look to make sure that all the categories are covered, but I'm not going to get into it with scrutiny. But it's a good idea for you to do a good job on that because you get to use the notebook in the final. Okay? Any questions about last week's lab? Okay, I'm hearing crickets out here. Somebody at least say something.
I was struggling like a quiz.
Saki, you were struggling with what?
The quiz.
The post lab?
Yeah.
What was
I just like so confused after all. And I still not understanding yet.
They should be, Saki, they should have been just straight. Let me unshare this. I'm going to go through and look. They should have been just straight ideal gas law problems.
Yeah, that's what I thought. But I don't know. I just so get confused. And I just didn't get the.
Okay, I'm pulling it up now.
Mm-hmm.
Do you mind if I publish yours?
Yeah.
Okay, it was post lab for gas laws.
Right.
Anybody else have trouble with them? Saki, the main problem when you're dealing with gas laws, okay, there's just 2 questions.
Yes.
Okay. All right, Saki, gas law problems.
Mm-hmm.
If nothing changes, you have 4 parameters you're dealing with gas laws. You're dealing with pressure, volume, moles, and temperature, right?
Yes.
If nothing changes, pressure, volume, temperature, if those things do not change, use the ideal gas law.
Okay.
All right. If something changes, then the things that are changing are the gas law you're going to have to use. Does that make sense, Saki?
Yeah. Mm-hmm.
All right. This one, first one is just sorry, I'm looking at this question. Okay. I'm going to have to get out of here because what he does, all right, what he's done is he's changed the numbers. So I can't do it where I'm in the screen I'm in.
Okay.
So I am going to have to look at your direct thing. Guys, I'll get to this. I'll get to the course today. It should not take us that long. It took me like 45 minutes last night. So just bear with me for a second. Oh, you got half of the problems right, Saki.
Yeah.
All right. First problem.
Mhm.
You're given the gas constant, you're given grams of dry hydrogen, you're given the pressure.
Mhm.
Okay. And you're given the temperature.
Yeah.
Simply speaking, that's PV equal nRT. I think you got it right. So
Yeah.
it would be change the pressure to 2 atmospheres.
Mhm.
You change the C to Kelvin,
Yes.
and you change the grams of hydrogen to moles of H2, which I
Yeah.
think you did it correctly.
Yes.
All right, let's see the second one. All right, so the second one you're trying to calculate for R. Okay, Saki?
Yes.
So you have PV equal nRT, or PV divided by NT is equal to R. Does that make sense, Saki?
Yes.
All right. You're given dry hydrogen gas. That means there's no water vapor, so you don't have to subtract anything out. You take this number to 738.3, you divide it by 760, that gives you your atmospheres.
760.
You take your temperature, 23.50,
Mhm.
add 273.15, and that will give you your Kelvin.
Okay.
All right, mass of magnesium. You have to understand, Saki, in the equation, magnesium plus HCl yields MgCl2 plus H2. The ratio between magnesium moles and H2 moles is the same. It's a
Yes.
1-to-1 coefficient. So
Yeah.
you take the mass of the magnesium, divide it by the atomic weight, which is 24.31. That gives you the moles of magnesium, which is equal to the moles of hydrogen.
Mhm.
The only real conversion you have to do is the volume of the H2.
Mhm.
Okay. And it's saying you have 42.60 ET units.
Yes.
Well, to get real milliliters, you have to multiply that by the 0.8282 milliliters over an ET unit.
Yes.
All right. So you have your volume, moles, temperature, and pressure. You just plug it into R is equal to PV over NT. You got it now?
Yeah, I got it now.
Okay. Anybody else have any other questions, guys?
Um,
Or you just want to get the hell out of here this morning?
Could be.
Okay, Saki.
Yeah. Okay. Thank you so
Saki,
much.
do you cook at home?
Not really.
All right. Do you know the difference between using an aluminum and a iron pan?
Mm-mm.
Okay. Anybody cook? Anybody cook with iron pans and versus aluminum pans? Nobody? You slugs just let somebody else cook your food for you?
Yeah.
Anybody know
Um,
anything about iron pans? Okay, I can't bring it home. All right, you're going to have to trust me on this one then. If you put an iron pan on, this is a story. I used to have a horrible time making hash browns because I was using an iron pan. Iron absorbs and keeps heat much longer than aluminum does. So in effect, what was happening was because I was using an iron pan, I was getting the potatoes too hot and I was burning them. So the type of substance has something to do with the amount of energy that gets absorbed or transmitted. Carson, have you ever made pasta?
yes, sir.
All right, you're making pasta for yourself, right?
Hmm.
Maybe use what, half a pound of pasta?
Yeah.
Half a package?
Mhm.
Okay, you put it in there. You can use generally like a quart of water, right?
Yeah.
All right, Carson, if you were making pasta for the whole family, all right, you'd use like maybe 1 or 2 boxes, right?
Probably. Yeah.
Would you have to use more than a quart of water to do that?
Um.
Say yes,
I
Carson.
I would assume so.
Yes,
Yeah.
okay. Now, would it take longer to heat the pasta pot you're using to make the pasta for your family? Would it take longer to heat that up or your quart?
Probably the larger one.
Because you've got to heat up more mass.
Mhm.
So the amount of substance has something to do with the energy that's absorbed. Thank you very much. Aditya. Aditya.
Yes.
Okay, Aditya. Have you ever taken a bath in your life?
Yes.
All right, good, good. All right, now imagine you fill up your bath. Do you like it kind of tepid or do you like bath water really hot?
Like kind of medium, like not too hot or cold.
Okay, not too hot, not too cold. Okay. When you boil water, is that really, really hot?
Yes.
Are you going to put your little tush in boiling water?
No.
No. So, do you think it takes more energy to heat up water to boiling or to heat it to your nice little tepid bath water?
More time to boil.
All right. So there are three factors we have to deal with when we are dealing with energy. We have to deal with the substance, the type of substance we're dealing with. We have to deal with how much of that substance we're heating up, and we have to deal with the degree to which we are heating that up. If we're heating it to a higher temperature or a lower temperature. Those three factors are involved in determining how much energy is going to be required. Does that make sense, everybody?
Yes.
So I got a slideshow, current slide. All right. So the equation we've come up with for the amount of energy that is dispersed in such a system is the energy Q is equal to the mass of what you're trying to heat times the specific heat. The specific heat is a constant that is related to the type of substance it is, times the change in temperature, T final minus T initial. Everybody's buying this formula, right? By the way, it's a general consensus that students in Chem 1 hate thermodynamics more than any other subject. Is that true with you guys as well? Yay, nay?
Yeah,
Yeah, as of right now.
I would agree.
All right, so we have that general formula. Energy, we'll get through this, guys. We will get through this. Our energy is equal to mass times specific heat times the change in temperature. You may recognize this formula as Q is equal to MCAT, MC delta T, right? Is that how your professor has shown it?
Yeah. Mhm.
The reason I do MS delta T is because C can be the calorimetry constant. If you've heard about that, then you know what I'm talking about. And I just like to distinguish the specific heat from the calorimetry constant. Does that make sense, guys?
Mhm.
All right. Now, you have a piece of metal. How are you going to get the temperature of that piece of metal? Is it going to be easy? Can you
No.
shove the thermometer in the metal?
No.
So basically, you can't really get you can get the mass. And if you know what the substance is, you know what the specific heat is, but you can't really get accurate temperature readings, right? So we got to do this by another means. We have plenty of water in the world. Water has a fairly stable specific heat. So what we do in these circumstances is we measure what happens to the water and then we apply it to what happens to our system. And what you have to understand is the water surrounds your system. So it is going to be the Q of your surroundings. The system is whatever you're putting in the water. Now, if the system gains energy, that energy has to come from somewhere. Where it comes from is the surrounding water. So if your system gains energy, your water loses it. Your water goes down in temperature. If your system loses energy, gives up energy, then what happens is your water is going to take that energy in and absorb it. So your water is going to have more energy than it did before. The temperature is going to go up. Does that make sense, guys?
Yes.
So in effect, what I'm saying is the Q of my system is going to have the same value as the Q of my surroundings, but it's going to have a different sign. Q of system is equal to negative Q of surroundings. Are we good with this so far, guys? So what we're going to do in these experiments, we're going to measure the change of temperature for the water. We are going to measure the mass of the water, and we're going to know the specific heat of the water. So we're going to know how much energy the water gains or loses. Since we know how much energy the water gains or loses, all we have to do is take the negative of that value, and we know the energy of our system. Okay, we have some data here. What we're going to do is we're going to measure a calorimeter dry. Styrofoam cups, they weigh 2.5609. Then we're going to put some water into the calorimeter, and we're going to measure the water and the calorimeter. Okay, guys, how do we get the mass of the water?
Subtract the mass of the empty calorimeter.
We're going to subtract the mass of the empty calorimeter from the calorimeter and water. Okay, now we don't want to put any water on the metal, because if we put water on the metal, that will change the mass of the water in the calorimeter. So what we want to do is we want to heat that metal in a test tube. All right, so we're going to get the mass of the tube and metal and the mass of the tube. We subtract those two, we get the mass of the metal. So the overall thing, what we're doing, you're going to weigh the tube and weigh the tube and the metal, get the mass of the metal, then you're going to put that tube with the metal into a beaker of boiling water, and you're going to let it stay there for about 15 minutes so that the temperature of the metal equals the temperature of the water. Are we good with that so far? All right. In the meantime, you are going to put a thermometer in the water, and that's going to be your initial temperature of the water. You're going to put a thermometer in the boiling water. That's going to be your initial temperature of your metal. Then, as quickly as you can, you're going to take that test tube out of the boiling water, and you're going to dump the metal into the calorimeter, put the lid in, and you're going to shake it around until you get the temperature of the water to rise no more. What you have to understand is happening is the metal loses temperature. That is an exothermic reaction. The metal is losing heat to the water. The water is gaining heat, so the water temperature is endothermic. Endothermic has a positive energy gain, exothermic a negative energy loss. So what happens is the metal keeps on losing heat, keeps on losing temperature until the temperature of the metal equals the temperature of the water. And in this particular case, we got the final temperature of the water to be 29.0 C. Everybody understands the experiment as I've described it. If you don't, please tell me now.
I'm sorry, could you just separate the exothermic and endothermic in comparison to the Qs?
Okay, Faye. The metal is hot, right?
Yeah.
Okay. When you put the metal in water, doesn't the metal lose its heat?
Yes.
So the heat is given up by the metal.
Mhm.
Isn't that an exothermic process?
Yes.
All right. So I'm going to explain this in a second again, but the initial temperature of the metal is more than the final temperature, right, Faye?
Yes.
So the sign of delta T is going to be negative, correct, Faye?
Mm-hmm.
Which is in being consistent with that being an exothermic reaction.
Because it loses energy.
It loses energy. The metal is losing energy because the temperature of the metal is decreasing.
Okay, thank you.
At the same time, that energy had to go somewhere. That energy went into the water surrounding the metal. So in
Mhm.
effect, the temperature of the water went up. So T initial is less than T final. So the delta T is a positive number.
Mm-hmm.
It gained energy. When it gains energy, it's endothermic. That is a positive number. Is that good now, Faye?
Yeah, thank you.
All right. Ultimately, what we're trying to do, we know the mass of the metal. We don't know the specific heat. We know the final temperature of the metal and the initial. We know the mass of the water, the specific heat of the water, final and initial temperatures of the water. We can set it up in this big equation fashion, but I don't like to do that because I think this big equation thing is confusing as hell. So what I'm going to do is I'm going to break this up into two processes. Whatever. I'm going to break it up into two equations. First, I'm going to determine what the Q of my water is. Then I'm going to turn my Q of water into Q of metal. Then I'm going to solve for using the Q of the metal. I'm going to solve that equation for the specific heat. Everybody understand the strategy where I'm going here? So my Q of my water is going to be the mass of my water times the specific heat times the change in temperature. My mass of my water is 43.5994. My delta T was 5.0 grams Celsius. Okay, write this down, guys. In 99% of calorimetry problems, your significant figures are going to be dictated by delta T. So all you're going to have to do is look at delta T, determine how many significant figures delta T has. That's going to be the significant figure of your final answer. Okay, I have the mass and the delta T. All I got to do is plug it into my equation. I do this, and you see I've already screwed up. And show, because I used three significant figures. So I do the math out. I multiply the mass times the specific heat times the change in temperature. I get a positive 910 joules. But I have to realize Q of my surroundings is equal to Q of my system. My system is the metal. So my 910 is equal to my Q of my metal, which is a negative 910. Now I have to look at what happened to my metal. Initially, my metal was at 98.4 Celsius. The final temperature of the metal is simply the final temperature of the water, 29.0. So to get the delta T, I subtract 29 and 98.4. This gives me a negative 69.4. And I figured the mass of the metal by subtracting out the test tube, that was 60.9267. Again, I'm going to use Q is equal to MS delta T. But this time I'm substituting the metal parameters. So I get negative 910 is equal to the mass of the metal times the specific heat, which I'm solving for, times delta T. Negative, negative, my specific heat ends up being positive. I divide the 910 by the mass of the metal and then divide it again by the specific, or by the delta T. I get my specific heat to be a positive 0.216. Everybody with me? Okay. Now we're going to get everybody like magic,
Yeah.
because the next thing has no basis that I can find of any scientific reality. The guy that came up with this played with numbers. And by trial and error, he found out that the molecular weight is equal to 25 divided by the specific heat. I could find no basis, no theoretical reasoning behind this. It's just the way it is. So in order to get my molecular mass, I'm going to take 25 divided by the specific heat I just came up with, and I end up with 116 grams per mole. Now all you have to do is go to the periodic chart. If I'm not mistaken, this turns out to be 10. I could be wrong about that, but all you got to do is look at the periodic table, find out which atomic mass matches 116 or is at least close to it, and you've identified your metal. Part A is done, guys. Any question about part A? Okay, part B. Part B, what you are doing is you're trying to ultimately determine the heat per gram of dissolving a salt. So again, you have to figure out what your system is and what your surroundings are. In this case, your system is the salt dissolving. Your surroundings are merely the water that is involved in this as well. So your water is going to gain or lose heat depending upon whether it takes heat to dissolve your salt or whether dissolving the salt is exothermic. So do we understand what's happening basically in this particular experiment? We good? All right, so in this instance, we put water, we measure the calorimeter again, put the water in, we subtract the two, we get the mass of our water. We measure our initial temperature of the water. All right, then we're going to take a beaker and measure it. We're going to put some salt into the beaker and measure that amount of salt. We are then going to quantitatively transfer the salt into the water and measure the temperature. In this particular instance, it took energy to dissolve the salt. That was endothermic. Dissolving the salt absorbed energy. That energy had to come from somewhere. It came from the water. So the water lost degrees Celsius. It went from 24.1 to 16.3. Again, guys, we're going to use our Q is equal to ms delta T. And our this is going to be for our water. So our mass of my water is 50 degrees. My delta T is a negative 7.8 Celsius. So my Q of water is equal to my mass times the specific heat times my delta T. I get a Q of water of being negative 1600 joules. Remember, my system is the dissolution of salt within that water. So it's going to be a negative sign from the Q of the water. So my Q of dissolution is 1600 joules. Okay. Now, what this is saying so far is that it took 1,600 joules to dissolve 10.060 grams of your salt. It's simply asking how many joules is it going to take to dissolve 1 gram. So we take the total number of joules, divide it by the total number of grams of salt, and we get 160 joules per gram. Easy error, guys. Easy error. When we're at this step, you have 2 masses to choose from. You have the mass of the water and you have the mass of the salt. You have to realize that when you're in this step, you are trying to find how much energy the water is gaining or losing. So you have to use the mass of the water. Do you understand that? Carson, shake your head, yes.
So mass of the water, not mass of the solution, because the salt's in it.
No. It is the mass of the solution. The salt is
Oh.
in the solution. Well, Faye, you bring up an interesting point.
I'm just looking at the calculated data page so I can write a note for myself.
Okay,
later.
Faye, what do they use in the calculated data page? Do they use the mass of the solution or do they use the mass of the water?
Oh no, I'm looking at the blank table. I'm just so I can, that's what I was asking. Is it the mass of the water or total mass of the solution?
To be honest, yeah, I understand. Perfect.
They make it,
Faye, no, I know exactly what you're saying, Faye. And that is a perfect question. Absolutely tremendous question. And you know what my answer is going to be? My answer is going to be like the underwear I'm wearing right now. Depends. I just had the thing. I just had the operation, so I have to wear Depends for the next couple weeks. Bad joke. Okay. It depends upon who you're talking to, Faye. I literally went to clarify this with 2 different professors. One gave me one answer, the other gave me the other answer. So we are going to be consistent, okay? When we are doing this, the mass is going to be just the mass of the water. Okay, Faye?
without the salt.
The salt we're going to use later.
Okay, alrighty, thank you.
So when we're determining the energy that the water gains or loses, I just want the mass of the water. Okay? That will give
Okay.
us the energy that the water gains or loses. We then, Faye, we're then going to use the mass of the salt to determine, we're going to use the mass of the salt to determine how much energy per gram there is. Does that make sense, Faye?
Yes.
Ultimately, Faye, I think you are right. I think it would be probably better to use the mass of the solution. But again, I'm getting conflicting results, conflicting opinions on that. So basically what I've decided to do is I've decided to just say, okay, the first step, just mass of water.
Okay.
If you use the mass of the solution, you will not get it wrong. Okay?
Thank you.
Last problem. Last problem, we're going to determine the enthalpy of a reaction. And the reaction we're going to use is HCl and NaOH. You're going to take 50 milliliters of 2 molar HCl. Again, this may change when you go look at the exact experimental data to determine this. I'm just pulling these numbers out of a hat. You're going to take 50 milliliters of 2 molar HCl and 50 milliliters of 2 molar NaOH. Now, what you have to understand is the overall reaction is 1 mole of NaOH reacts with 1 mole of HCl. The molar ratio is 1:1. There's a 1:1 stoichiometry. So I've got 0.1 moles of HCl and I have 0.1 moles of NaOH. They both limit each other. Okay, That's the first thing we have to understand. Second thing we have to understand is that we're heating up the whole solution. So I'm heating up. After I mix them, I no longer have 50 mils of HCl and 50 mils of NaOH. I have 100 milliliters of the solution. Okay? Now, the density of that salt solution is 1.02 grams per milliliter. So you have 50 milliliters and 50 milliliters. You have 100 total milliliters multiplied by the density. That will give you 102 grams as the mass of our solution. We good? So simple. And the other thing that's strange about this is no matter how many times you do this, no matter how long you leave out the base and the acid, somehow the initial temperatures of the base and the acid are always different. So to do the initial temperature of our solution, we're just going to average the base and acid solutions. In this particular case, the average is going to be 23.3 Celsius. Then we've got our acid in our calorimeter. We're going to pour our base into it. Put the lid on, and we're going to swirl it around until we get the highest temperature. That turns out to be 37.4 Celsius. So to get the Q of the water, that's simply going to be 102, the mass of the water, times the specific heat, times my change in temperature. I do this math out, and I end up with 6,060 joules. In this particular instance, we're trying to find enthalpy. Enthalpy units are kilojoules per mole. So the first thing I have to do is I have to change my Q of water into my Q of my reaction. My reaction is my system, the water is the surroundings. So my negative, or my 60.60 joules becomes negative 60.60 joules. The next thing I have to do is I have to convert joules to kilojoules. I do that by multiplying 1 kilojoule over 1,000 joules. But remember, we're trying to figure out the enthalpy per mole of reaction. And remember, the moles of HCl and the moles of NaOH are 0.1 each. In this instance, we're looking for the limiting reagent. Both of the limiting reagents, so I use one of them. The amount of moles of my limiting reagent is 0.100 moles. So I take my negative 6.06 kilojoules, divide it by 0.100 moles. This gives me a result of 61 kilojoules per mole. Questions, guys? I'll make sure that this PowerPoint is loaded up. Literally speaking, the equations are just the same. All right. Any questions about what we've done in the 3 experiments?
For part C, I just want to make sure I heard this right. You added to get the mass of the solution, you added the 2 volumes, converted it to liters, and then you multiplied the amount
Faye.
of liters.
No, Faye.
Oh.
You don't convert it to liters.
Oh.
Because in order to get the mass, you're multiplying it by the density, which is 1.02 grams per milliliter.
Multiply it by the added milliliters.
You multiply the density by the milliliters that are added together.
Okay. Okay.
Do not convert to liters.
Okay. Alrighty.
All right. Then the last step, you're only using the moles of one of the 2.
The H plus, or does it not matter?
It doesn't matter because they're going to be the same.
Oh, it's 1.
They're both going to be the same number of moles.
Okie dokie.
Any other questions, ladies and gentlemen? Okay, I'm going to go take you through the, nope, that's not it. I'm going to take you through the report. And the report pretty much is pretty much straight thinking, straight process. Sorry, it's taking so long. My computer is slow today for some reason. All right. Question 1, you get a free 5 points. Make up a number. Okay. Question 2. You know the mass of the calorimeter. You know the mass of the calorimeter in water. Give me the mass of the water. You know the test tube weights and the test tube and metal weight. Give me the mass of the metal. You're going to have to show me what the change in temperature is of the water and of the metal. If you have questions, I'm going through this fairly fast because I think it's fairly easy. Q of the water. You know the mass of the water, you know the specific heat of the water, and you know the change in temperature. Give me the Q of the water here. Specific heat of the metal. Once you get the Q of the water, make that number into a negative because Q of surroundings is negative Q system. Then you've got the specific heat of you've got the Q of the metal, you know what the mass of the metal is, and you know what the delta T of the metal is. Solve for the specific heat. I don't know whether you have more than one trial or not. If you do, give me the average. If you don't, just report out what the one trial value is. And it's another easy 5 points. All right, that's all you had to do from part A. Part B, unknown number, a free point. Mass of water used. Again, calorimeter and water minus calorimeter. Mass of the solid used. Beaker and salt minus beaker. Okay, delta T for the solution. Get the temperature. Question?
Yeah, I have a question. The mass for the number, the one you just did, 5. They just gave us a mass. They
Then
didn't
just
do
give
any-
it. Then just give it, Faye.
Okay, all right. Just check.
Don't worry about it. Faye, before I do these problems, okay, I go through and do the calculations myself so that I can quickly grade your reports, okay?
Okay.
So I'm going to see that they just gave you the mass of the metal. Don't worry about it, or the mass of the
Okay.
solid, okay?
Thank you.
So you're going to do the temperature beforehand, the temperature after you add the salt, that's delta T. Solve for the Q of the solution. Okay. Then the Q of the unknown is just going to be negative the Q of the solution. Then once you have the Q of your unknown, all you're going to do is dissolve it by the number of grams of the salt. Are we good there? You don't do multiple trials, so don't worry about E. Heat of neutralization. Take the average initial temperature and subtract it from the final temperature. That will give you a change in temperature. Q of solution. Milliliters times density, 1.02, will give you the mass of your solution. Multiply that by water, multiply that by your change in temperature. That will give you your Q of solution. Q of reaction is negative that. Then what you're going to have to do is take your Q of reaction, divide it by the number of moles. This is misleading, guys. This is misleading. It's either the moles of H plus or the moles of OH minus, not the combined. Okay? And make a note of that because I've specifically told you about that. So if you give me the addition of moles of H plus and OH minus, I'm going to mark it wrong. It's just the moles of OH plus or OH minus. And that's the last of the report. Any questions on the report itself? All righty. Now I'm going to do the post lab real quick and we'll be out of here. Okay, first sample. By the way, these numbers do change. It gives you the mass of the metal and initial temperature of the metal. It gives you the calorimeter weight, initial temperature, and final temperature of the calorimeter after the metal's been adding. So all you want to do is you want to turn, first of all, the first question is easy. Give me the change in temperature of the water. Second question, change in temperature of the metal. Third question, Q of the water. Take the mass of the water times the change in temperature times 4.184. Last question, calculate the specific heat of the metal. This is only simulating the experiment you just went through, part A. Any questions on this, guys? Faye, you're out of questions?
No, I was gonna wait so people could leave.
Okay, guys, that's all I have. I got you out of here in less than an hour. Okay, Faye, nobody seems to want to talk, so go ahead.
Okay. For part C, could you just talk through the heat absorbed by the solution and then heat released by the reaction? I just
Okay,
don't know what.
no,
goes.
hey, Faye, thermodynamics is the reason I am not a physical chemist. I really, when I was going through this and like in your situation, where I was just taking like my Chem 1 class, I really thought, you know, this stuff is really, really interesting. This is a part of chemistry I really like. Then I got into thermodynamics and I decided, okay, there's too much math involved.
Yeah.
And if you think this is bad, you ought to try and do it with calculus. So I'm sorry, I'm going to stop share and bring up the PowerPoint again. All right, you seeing the PowerPoint, Faye?
Hmm.
All right. All right, you're talking about the reaction, right, Faye?
Yes.
All right, when I put HCl and NaOH together, the thing that's creating the heat is the actual reaction of NaOH and HCl. Do you buy that? Faye?
Yeah. Sorry, I muted. My dog was gonna bark.
I've got dogs all the time. Just go ahead and let her.
Okay.
Did you understand that the heat that is generated is actually the byproduct of taking NaOH and reacting it with HCl?
Yes.
So that is my system.
The
The
system is
actual reaction is my system. Okay? But
okay.
that reaction is not done in a void. That reaction is done with a whole bunch of water around it. The water surrounds the reaction. So the water is my surroundings. My system is the actual reaction, NaOH plus HCl. That's going to, if it's an endothermic reaction, it's going to absorb heat from the water. If that is an exothermic reaction, that's going to give heat and the water is going to absorb it. Does that make sense, Faye?
Yeah, but I thought the reaction produced the H2O.
It also produces energy.
Okay.
All right. Okay. Let me put in a new slide here. And this is going to be important when you get into Chem 2. It's an important concept. Nope, I don't want to copy. I want a new slide. All right, so we have A plus B reacting to make C. Okay, we have that?
Yeah.
All right. If I have an exothermic reaction, Faye, does that release heat or does it absorb heat?
Releases heat?
Releases heat. So in effect, heat becomes a product. Doesn't it?
Mm-hmm.
All right. If I have an endothermic reaction, don't I have to have heat in order for the reaction to go?
In the reactant side? Yeah.
And heat becomes a reactant. So if you want to think about it that way, Faith, you can think of the energy as being either a reactant or a product based upon what the reaction does. If I mix two chemicals together, okay? Let's go through another scenario, okay? And you're gonna, if you haven't gotten into this already, all right, say we have a double displacement reaction, okay? What's really happening? I have a bond between A and B, right, Faith?
Mm-hmm.
I have to break the bond.
Mm-hmm.
All right, and I have to sit here and think of this. So breaking bonds takes energy,
Yes.
right?
Mm-hmm.
So this is a positive Q. You have to put energy in order to break that bond. Does that make sense, Faye?
Yeah, but then I lost you with the Q. Why it's positive.
Q's
'Cause you're
energy. Why it's positive? Because I have to put, the system of A and B has to absorb energy to break A away from B.
Okay.
All right, let me give you an example. All right, you have water, H2O, right?
Mm-hmm.
So in order for me to go from water to H2 and O2, I have to break the two OH bonds, right?
Yeah.
All right, if I'm breaking those bonds, I have to put energy in to break those bonds. That means
Yeah.
my overall system is going to have more energy before I broke the bonds than before. So what I'm saying is O2 and H2 gas have more energy than the water molecules. Does that make sense now, Faye?
Yeah, that makes sense.
So I had to put energy into the H2O to break those bonds to make H and O separate.
Okay.
All right. Same instance. My CD. I'm breaking that bond. That also takes energy. I have a positive Q2. All right.
Mhm.
Now, when I form bonds, that's an exothermic process. So when I make AD, I am forming a bond. Energy released. So that's a negative Q3. Same thing when I do C-B. That's forming a bond. Energy is released. Negative Q4. So my overall reaction energy is going to be equal to negative Q4 plus a negative Q3 plus my Q1 plus Q2. All right, would you buy that, Faye?
Yeah, I just did that in my chemistry lecture class.
This is, Faye, this is why I'm trying to go over this with you, because it seemed like you didn't understand it. That's why I'm going into this kind of detail.
Yeah,
All
I
right.
didn't do well.
All right, so if I add this,
Mhm.
if Q4 plus Q3 is greater than Q1 plus Q2, I get a negative answer. The overall reaction is exothermic. Does that make sense, Faye?
Yes.
What it's saying is that forming the new bonds released more energy than it took to break the original bonds. And if that is the case, you have an overall energy release, which means it's going to be exothermic. On the other hand, if Q4 plus Q3 is less than Q1 plus Q2, my answer is going to be positive, and that is going to be endothermic. Is this kind of putting things into place for you?
Yeah, a little bit. I
Right
think
now, what I think you're doing is you're in the process of adding the individual bond energies. Am I correct, Faye?
yeah.
And you're wondering why Hess's law said you subtract them, and this one
Yeah.
you're adding them. Is that the case?
Yep.
All
Mhm.
right. The reason you're adding them now is because if you notice, look at that chart where you have the individual bonds like CC, CH,
Yeah.
those bonds. Aren't all of those positive numbers?
I believe so.
All right. So because they're all positive numbers, that's why you have to do it this way. If you look back at Hess's law, you have some enthalpies that are positive and some enthalpies that are negative.
Mhm.
And that's why you have to subtract them in that instance. Hess's law, you're going to be subtracting. In the bond energy thing, you're going to be adding them together.
Okay.
That makes sense?
Mhm. Yeah, it's a little more clear. I think just the concept of the positive and negative, I think I'm not thinking about it like it's not thinking about it the right way. If that makes sense.
Well, what you're doing in the second instance, if you're breaking bonds, you make those negative, right? If you're
Mhm.
breaking bonds, I'm sorry, if you're breaking bonds, it's a positive. If you're forming bonds, that's a negative. That's where the
Because
positive and negative come in.
because the amount of energy that it takes, right?
Well, no, it's just because of the fact when you break bonds, it takes energy to break bonds. When you form bonds, energy is released. So if energy is released, that's exothermic. That's a negative sign. If you're putting energy in, that is endothermic. That's a positive sign.
Okay.
Give me a second, Faye, okay? I want to make sure that I'm doing this correct for you, all right?
Okay.
What chapter are you in?
Let me get to the home page.
11? Is it at the end of 11 or 10?
Hold on a second. She just
I'm not seeing it in 11. Okay, it's probably in 10. Yeah.
She doesn't have numbers. She just has module numbers.
All right. You're not dealing with the book at all?
No. No.
All right.
Yeah, sorry.
All right. And by the way, I was correct. And when I've been explaining this, what's on the screen right now is absolutely correct.
Okay.
All right. All right. What I want you to do right now is I want to bifurcate your mind. Hess's law, one part, bonds, another. Okay.
Mhm.
And we're just dealing with bonds themselves. Okay.
Yeah.
All right. So the rule when we're just dealing with bonds, the sum of the bond energies that are broken plus the sum of the bond energies that are formed.
Mhm.
All right. That's the overall equation that you're using when you're dealing with individual bond energies. Does that make sense to you?
Yeah.
All right. When you break bonds, it takes energy. All of the bonds that are broken are positive. Okay, Faye?
Mhm.
If you break a bond, if you have, all right, look at it this way. If you're looking at the reactants, you're going to have the bonds that have to be broken in order to form the products, right?
Yeah.
In order to break those bonds, it takes energy. So every time you break a bond, that bond energy is going to be positive because you're breaking it.
Mhm.
Now we're going to look on the other side of the arrow. When you form bonds, that releases energy. So every time you form a bond, it's exothermic, and those are going to be negative. All right, let's work a problem out. All right. By the way, guys, anybody, Carson?
Yeah, I was just gonna ask really quick. I did my notebook for the gas constant,
Yep.
but I completely forgot to submit it. So is it okay if I could email it to you just
No.
for the feedback part?
Okay.
Like whenever,
Faye,
like
hold
today,
on
I'll,
one sec. Faye, hold on 1 second. Okay.
Okay.
yeah, I have it right here.
No, no. Okay. Trying to figure out where I'm at. Yeah. Okay. And this is notebook for gas law constant, right?
The last one, gas constant.
All right. You're seeing what I'm doing, right?
Mhm.
You have until 5 to submit it. Okay.
Thank you very much.
All right, Faye. Samir? Samir.
I know.
All right, you got in here late. You're gonna have to look at the video, all right?
I understand.
Okay. All right.
I'll
Gonna
leave
stop.
you to help Faye since
What,
no
Samir?
I said I'll just leave you to help Faye so since there's no.
No, that's up to you. But if this is gonna do you good, you're more than welcome to stay.
I might as well. It never hurts to get some extra knowledge.
Okay, Faye. I have a reaction. Okay.
Mhm.
I'm taking CH4 out. I gotta make sure I got this right. One C, 4 H's, 4 O's, 4. Okay, we're good. We're balanced. All right. Can you see, in order to go from methane and oxygen to carbon dioxide and 2 waters, I need to break 4 CH bonds. Are you seeing that, Faye?
Mhm.
And I have to break 2 O because oxygen to an oxygen is a double bond.
Mhm.
All right. But I'm forming. All right, let's look at my CO2. Do you remember what a Lewis dot structure of CO2 is?
I believe so. See. isn't it a double bond?
2 double bonds.
Yeah.
Okay, so when I'm making CO2, I'm making this compound, right? Right?
Mm-hmm.
So in order to make this compound, I've made 2 C double bond O's, right?
Yeah.
All right. And I'm forming with H2O. How many OH bonds am I forming with H2O?
H. 4.
All right, so this is basically, when you're doing a problem like this is how you have to break it up. Does it make sense, Faye?
Mm-hmm.
All right, now, if I am breaking bonds, that's positive. Right?
Mm-hmm.
I've got 4 CH bonds I'm breaking, so that's a positive 4 times 414 kilojoules per mole.
Yeah.
I'm breaking 2 O double bond O's. So this is a positive 498. 2 times 498, right?
Mm-hmm.
Now I'm forming 2 C double bonds. So that's going to be a negative 2 times C double bond to O. Where's that at? 799.
C double O.
C double bond O. If you look in your chart,
Oh, I'm trying to go look at my quiz that I failed. So.
basically, since carbon dioxide is such a stable molecule, it has a little bit extra energy to form or break that bond, other than just a straight C double bond O. Does that make sense, Faye?
Mm-hmm.
And my 4 hydrogens are a negative 4 times 464. All right, does this make sense to you, Faye?
Yeah.
So overall, I'm going to have a positive 4 times 414 1656
Mm-hmm. 2 times.
plus 2
26,
times
50.
498, 996
Mm-hmm.
plus 2 times 799, 1598, a negative 1598 plus a negative 4 times 1856. Do you see how I got that, Faye?
Mm-hmm. Sorry, I have to say bye to my mom 1 second.
No.
She's
Did-
in town for the weekend. Let me just hug her. Bye. Love you. Okay, sorry.
All right, so does this make sense?
Yeah, I think I was confused because from what I understood from the videos that I watched for my lecture class, they said in my notes I put delta H for the bond energies equals the sum of bond energies of the reactants minus the sum of the
There are
bond
two
en-
rules, okay? We're dealing with two rules. Right now, we're dealing with bond energies, individual bond energies.
Mhm.
And when we're dealing with individual bond energies, all of the bond energies are listed as positive values. You
Uh-huh.
have to make the determination as to whether it's going to be a positive or a negative by determining whether you're breaking the bond or whether you're forming the bond. If you're breaking the bond, that's going to be a positive number. If you're forming the bond, that's going to be a negative value.
Okay.
Or in other words, I'm going to make a new slide. Your overall H, delta H, is going to be equal to positive sum of all bonds broken All right. This is not Hess's law.
Okay.
This is the doing enthalpy by individual bond forming and breaking. All right. Does that make sense, Faye?
Yeah, it does.
All right. That is different from Hess's law. Hess's law. The enthalpy is equal to sum enthalpy Okay. Would you buy that?
Yeah.
Two separate problems. Okay. I know it's kind of straining your head at this point, but you just have to go by the fact that when you're looking at that table for bonds, for the energy of the bonds, those are all positive numbers. And you are the one that's going to have to determine whether the sign is positive or negative based upon whether the bond's broken or whether the bond's formed.
Okay.
All right. Now, when
Which-
we're doing Hess's law, the individual, you don't have a book, do you?
No.
All right. Did she give you a table of the enthalpies?
No. But she gave us if you look at this on our quizzes, she gives us what we need for the problem.
All right, that's
So-
fine. That's fine enough. That's good enough. All right, give me a quiz problem, Faye, from your Hess's law. Give me a quiz problem.
Oh,
Is it a Hess's law or is it a bond breaking?
empathy from bond energy.
Okay, that's your quiz. That's what I just went over. Let me see if I can figure one out for you. We're gonna do,
I got the numbers wrong too, but I also didn't know what was negative and positive. I have one that's 2H single bond H.
2.
Mhm. Can you see it? I don't know if you can.
No, I can't.
Oh, okay. So
Again,
it's
again, Faye, are we doing a bond problem or are we doing a Hess's law problem?
bond energy.
All
It
right,
says using the bond energies below kilograms per mole, calculate the estimated delta H of the reaction pictured below the
what is the,
table.
give me the reaction.
2H single bond H plus O
2H2.
double bond.
Okay, 2
Yeah,
dash H
yeah.
plus,
O double bond O. And then product is 2 H2O, but it's H single bond O, and then another one.
okay, so again, if I'm doing this, just like I did it before, the way I would set that up is I would do 2 H bonds broken. 1 O bond broken. 4 H O bonds formed. You see how I got that, Faye?
Mm-hmm.
All right, now I go to my chart. All right, what does she have for HH bonds broken?
436. Oh, she doesn't have broken or formed.
Well, what does she have what's she have HH bond as? How much energy?
436.
Okay, I have 2 of them. And it's a bond broken, so that is a positive number.
Mm-hmm.
You said 436?
Yep.
All right. What does she have for an HH? An OO.
Double bond, 498.
And an OH?
464.
So that's how I would set up, this problem. Wherever the bonds are broken, I'm making sure that I call the bonds broken a positive number. Whenever the bonds are formed, I'm calling that a negative number. And all I'm doing is adding them all up.
Okay.
So do I need to go through and actually solve this today or?
No, no. Why did you say it's not the bond energies of the reactants minus the bond energy of the products?
Okay, because we're dealing with individual bonds at this point. All right, look at her chart. Look at her chart of bond energies. Are those all positive numbers?
Yeah.
So basically, what you are doing is you are making the determination as to whether that bond energy is going to be positive or negative based on the fact of whether you're breaking the bond or forming it.
Okay.
Breaking the bonds, you have to put energy in. It's a positive number. Forming the bonds, energy gets released. It's a negative number.
Okay. I think I get it a little more.
It's, believe me, Faye, if you think it's bad for you, I've been up in the front of a classroom and I have been sitting there and I've confused myself on this very issue because of Hess's law. So believe me, I sympathize with you, but you just have to release it and give it in that there are two different problems. Hess's law, you do sum of the enthalpy of the products minus the sum of the enthalpy of the reactants. Okay? Bond by enthalpy by individual bond forming, you have to realize that when you are breaking bonds, that is positive energy has to be put in. When you are forming bonds, energy gets released, and so that's negative energy.
Is breaking bonds will always be positive energy?
Breaking bonds will always be positive energy.
And forming is always negative.
Correct.
I think that, yeah, that makes more sense now to me.
Believe me,
especially
I know this is not an easy process. I really do know that it's not, because it's kind of like you're fighting against yourself.
Mhm.
You've learned something and you've committed to it and it's worked, right?
Yeah.
All your Hess's law problems, they've all worked. This is the way I do it. I have to do it this way. Then they throw a little monkey wrench in it. And when they do that, it kind of throws you for a loop because this is not the way I did it before. I did it before and I was successful. Now, when I do it, I'm unsuccessful. Why? It's because we're dealing with two different problems. Okay? And you just got to learn to solve Hess's law like Hess's laws are solved. Bond energies are like bond energies are solved. Okay?
Mhm. Thank you, Professor. That really, it really did help.
Good. Good.
I've been having trouble with that for a while, so.
Faye, believe it or not, this is why this is why I teach. This is why I teach for the aha moments. The money's just a sideline. Although I do need the money. Okay, if that's all, Faye.
Mhm. Thanks,
Uh,
Professor.
No problem. I get tired sitting in one position. All right.
Okay.
All right.
Go
So
walk your dog.
I'll talk to you later. I'll see you next week then. All right.
Okay, have a good weekend.
You have a good weekend too. Samir, you still out there?
Yes, sir.
All right. I hope that helped you as well.
It did. Thank you.
Again, Samir, you just have to deal with them as two separate problems. If they give you the enthalpy of the entire compound, you use Hess's law. If they give you the individual bond energies, you use the bond energy concept.
Okay.
That's the difference between the two.
All right. Thank you. Have a
You're
great
welcome.
weekend.
Look at the video for this, Samir, because it's not that intuitive. All right.
All right.
Okay. Take care, guys.